which is an unknown interior. So basically it can be made of neutrons, protons, electrons, hadrons, or more refined, more heavier particles. We call it hyperons, as I mentioned before, with the strangeness. So I'm talking about, if you never heard, but lambda, sigma, cascades, so heavier particles in the nucleon. Or we don't have hadrons. We just have matter, which is the confined quark and gluons, okay? Or even, exotic matter. Exotic matter, I mean, maybe even dark matter, if it accumulates. So people are also analyzing the possibility of having accretion of of dark matter inside these objects, okay? So here I'm showing more or less, let's say, exotic phases of what we can have in the interior. So we can have pions, kaons, those are called mesons, so quark and antiquark pairs. So mesons mean that they follow Bose statistics, while baryons follow Fermi statistics. And then they have all this Pauli blocking, like they cannot put together or in the same state with the same quantum numbers, the two baryons. So this is kind of Pauli principle. But anyway, what you can have there is then, neutrons, protons, electrons, muons. You can have hyperons. These are those hyperons that I was mentioning. This is called H-type baryon. It's a more, complicated structure, but you can also not have anything of that. You could maybe have quark matter, or maybe even your star is not only made of quark matter in the interior, but really after a very small area, crust, you have what is called strange quark matter. Okay, so this is an hypothesis, a metastable state, okay, of matter where you basically have deconfined matter. I'm going to concentrate first on nuclear matter, and then I will concentrate on hyperons. So let's start with nuclear matter, and then let's start first. What is the situation if inside a neutron star? So basically, what the reactions that dominate the scales of the dynamics is beta equilibrium. What it means, beta equilibrium? Beta equilibrium, when you talk only about neutrons and protons, involves these reactions. So basically, I'm having here neutron decay, okay, and what is called electron capture, electron captured by protons going to neutrons. Okay, so these are these kind of reactions that are in equilibrium. Okay, so we are talking that weak decay, that there are different forces, weak, strong, electromagnetic, okay? It's weak, strong, electromagnetic, and gravitation. So the weaks are the ones that are dominating here, okay, because of the time scales. So basically, these reactions, this equilibrium, is expressed in terms of what is called the chemical potentials, okay? The chemical potential is basically telling me the difficulty, the work you have to do to put a new particle in the system. So basically, these reactions mathematically can be expressed in terms of the relation between chemical potential of these particles. So the chemical potential of the neutron should be equal to the proton and the electron, okay? You can see that I forgot about neutrinos, because the idea is before, they really get into the equilibrium, those escape freely. So basically, they are not considered into this balance, energetic balance, okay? So basically, this is the relation between the thermodynamic quantities that happen here. You also have charge neutrality, so this implements a relation between the particle densities, because initially the object is charge neutral, and then at the end it has to be. And well, there is another conservation, which is the baryon number conservation. But actually, the two important ones for analyzing the equilibrium inside neutron stars are those ones here. Okay, so now I'm going to give you a formula about nuclear physics, but okay, it's just that what is the equation of state when everybody's talking about, and what are the bit of the characteristics, and what people look, experimentally, and what actually can be applied and used for neutron stars. So the equation of state basically is a thermodynamic relation, okay, between the variables that describe, as I'm writing here, the state of nuclear matter. So at zero temperature, you can do, an expansion in terms of the what is called the well, this delta parameter, which is telling me the difference, okay, between the neutron and the proton number. So of course, this is, you know, an expansion where you have only even terms, because this is due to the fact that the nuclear force is charge independent. So basically, it's approximately charge independent. It means that the interaction between neutrons and neutrons, neutrons and protons, protons and protons is more or less the same, okay? So, but why, once you have this expansion, you have here different terms that I expand now in terms of the density, okay? This is an expansion in terms of the density of the system. And I'm keeping low density. So basically, you cannot actually apply this expansion to neutron stars, but you can get information of those parameters that are really have to be constrained because of nuclear experiments. What are those parameters? Those are parameters, you know, you can do an expansion of this term here, this first one, which means the symmetric term. So here this delta is 0. So basically I'm telling you that I'm doing an expansion in density of this term of symmetric matter, so same number of neutrons and protons, while the second one, it's related with this asymmetry, okay, of the system, and you also do an expansion in density. So how do you understand all these different terms? So basically these terms here, this is called the binding energy of nuclear matter, okay? So at saturation density, at this density as this average density in a nucleus. And this is a value pretty well known. I will mention a bit some experiments. So this is something really that your model has to reproduce. So I'm saying, you know, you have an equation of state, you know how it should look like close, you know, to these densities for low densities. And this is one of the things that really has to fulfill in order to really go and say something about neutron stars, okay? You also have a second term, which you can see also it's an even term because this expansion is around a minimum, so there are no first order derivatives. So this is called the compressibility of matter, okay? This derivative is, you know, how difficult it is to compress, okay? And then you have also the other parameters for the asymmetric part. So the asymmetric part is this symmetry energy. Symmetry energy, the first one is at around this density, we do the expansion. This is telling me how difficult it is to put a proton, or to transform a proton into a neutron in the system. And then you have higher order derivatives. This is the derivatives of the symmetry energy and other higher orders. So what do we know? What are the constraints we have? So we have here constraints from nuclear physics experiments. So this is a typical plot that people do on the symmetry energy. Well, on the derivative of the symmetry energy versus the symmetry energy. Okay, this is, remember, this L is the derivative. Okay, is this one here. Why they do that? Because the first term, you know, the energy per particle, this is something pretty well known because of all the measured nuclear masses. So also the saturation, the exact value also because of electron scattering already from the 60s. So this is something we know. But then higher order, I mean, the next term in the expansion of the density, the compressibility, is something already that starts being something difficult experimentally. This is done through analysis. For example, they are called giant monopole resonances, so some kind of oscillations of protons and neutrons inside a heavy nuclei. We also have results, these are called heavy ion collisions. So still it's difficult experimentally to extract already, you know, the first term in this expansion, okay? In this expansion here of the symmetric part, it's still difficult to get information on that. And now we go to this second part, you know, the asymmetric part. And there, again, I mean, the first term is something that there are experiments, there is more or less well constrained also from nuclear masses, from, you know, some analog state phenomenology, some experiments, you know, that are, they are still being, you know, they are doing and trying to be more precise. So it's around 30 and 32 MeVs, but then higher derivatives, the L and other ones are not so well known. And this is the reason why there's one of these plots trying to constrain the L, okay, the first derivatives. And the first derivatives you can see here, for example, these are analyses, what they are called the electric polarizability on nuclei. Okay, so you have a band here of values from L depending on S. You also have these heavy ions, which is already this, let me see, this huge band here. And then you have neutron stars. And these are the different models, okay, where they are lying in this experimental area. You can see the variety of values still, you know, the bands that we still have. So, but still, I mean, you have, you know, as I said, you need some constraints from experiments, and experimentalists are doing the best, of course, to get really constrained this, because then your model has to fulfill this. Now, as I said, I mean, this is an expansion in low densities under all these parameters, but there are also constraints on the equation of state for higher densities, and those come from observations, okay? There is from the masses, there is values I show you that more or less, most of them were falling between around 1 and 0.5, but there's, you know, masses are around, you know, these values between 1.5 to 2.5, more or less precise. There is a need of neutron star radii, as I was mentioning before. So definitely it's difficult, but there is this, you know, momentum to really go for simultaneous mass radius measurements. I show you nicer, and I will tell you a few words at the end about EXTP. That's really what they are trying, you know, to have a same object, to have the mass and to have the radius with a 5%, with a 10%. This is what this error, this is what, you know, is where they are trying to get. Then we also have cooling, as I mentioned. So really the cooling, it's important, not only the equation of state, not only this relation with thermodynamic variables of energy versus particle density, or pressure versus energy, but really to have the composition, okay? So of course, depending on what you have a different pressure and different energy of the system, but you also need to know, according to your equation of state, which, when and how those different particles appear, the composition. Or also the superfluidity, whether, you know, sometimes the superfluidity doesn't affect the equation of state. The gaps are small, but still, you know, they have some important consequences for the dynamics of the object and for the cooling in this case. We also, you know, people debating whether, you know, moments of inertia, they can be observed. I don't know, I think they have been trying, I don't know how well the situation is right now. And of course, gravitational waves, okay? You can also think of other observations, but I just pointed out some of them, you know, that I'm here. Now, models. I'm just giving you an idea, okay? Of course, I mean, this is more for nuclear astrophysics experts, but this is just that, you know, there are usually two ways of approaching the problem. Usually the idea is really starting from what you know, what we call in free space. So basically the interaction between two particles. So the two-body, the three-body interactions when you only have two particles, like two nucleons. And then putting, you know, the effect of the whole system, in the sense that you don't have two particles, you have n particles, okay? You have a many-body system, that's what we call, okay? So there are different ways of doing that. There are different ways, and the problem sometimes is not only on the way of implementing this medium, but usually on how to build these interactions, okay? Because even for nucleon, we have problems. Why? Because when you get together two nucleons, you enter into this, you know, this repulsion, okay? This hard cold, this Pauli principle starts acting, okay? And then it's difficult to describe the interaction, okay? So there are different methods, okay? So for example, methods based on variational methods, quantum Monte Carlo, more diagrammatic expansions, or, well, more lately, these have been really put, you know, newly, what they are called renormalization group methods. So basically the idea is, well, to forget or somehow to integrate out this problem, this hardcore, and then analyze the low energy region. And of course, lattice. I mean, lattice is really trying, you know, to get from what they call first principles. So basically to build the interaction and then put all this many body system on top of it. What is the advantage? That you control this expansion, okay? What we call systematic addition. The problem, that this is difficult to go really high and high densities. This is what the neutron star requires, okay? So if you want to look, for example, at what we are dealing with, look at this plot here. This plot is the energy per particle as a function of the density. And those are different models. So you can see where we are in our world is around here, okay? Saturation density. This is around nuclei. But these are the densities probably that you need to describe a neutron star, okay? What is the difference between these color lines and non-color? Well, this is the effect of putting 3 body forces. So not to only have, for example, 2 nucleons interacting, but 3, okay? So therefore here is that. And of course, the difference between all these lines, when you only have 2 body, is the interaction itself. The problem I was saying, when you get closer to nucleons, you get into this region that's difficult to deal with, okay? But this is short distances, high densities. So this is the situation we have. Now, this is a way. There are other ways, like basically doing density functionals, okay? So we have density functionals that are adjusted to observables that I mentioned before, nuclear observables, but also observation, masses, if we had radius, also, you know, getting the right tidal deformability according to gravitational observations. And then you build up some kind of density dependent functional that could be non-relativistic, relativistic. So this, or you can even do in a statistical model. So there are this is a different way of approaching the problem. The nice thing is that you can really, because you're doing fitting some data, some observations, you can really deal with high densities. But the problem is that you lose predictability. So you basically, you know, systematically, you basically start putting terms to fit everything. And what do you predict? Okay. So, and this is something that you get into trouble. And again, just an example, I mean, these are, again, the energy as a function of the density. This means pure neutron matter, only neutrons, or this means symmetric matter. And you see also the range, okay? Here, more or less, all of them coincide because they reproduce nuclear data. But here, you can see we are extrapolating, okay? So there's a difference. We don't know, okay? Okay, but now, and then maybe last 10 minutes, and then I will stop, is, okay, this is just having the basic thing that you might think if you have hadrons. This is the first thing that you can have an idea when you start, you know, neutrons, protons, electrons. These are the first particles that people think of, okay? But now you can also go to more sophisticated, if you want, more heavier particles that are obtained in experiments, okay? And those are these ones. Those are lambdas, sigmas, and some others, okay? So you can see the masses. These are masses. This, if you don't know, the nucleon is around 1 GeV. So the lambda is 100, 130, okay? Larger, bigger, heavier. And the idea is that you might have, because the mass is not so different, to have these objects. And then instead of only having this, you know, these reactions, you might have reactions involving this, okay? Involving those strange particles. So this, everything was already in the 60s, okay? Already when they start, you know, I mean, the 60s also is when people start building these interactions of nucleon-nucleon. They also realize that, you know, there might be also lambdas and sigmas and hyperons, okay? So which kind of reactions I'm talking about? I'm talking about reactions of this type. I'm talking about reactions where basically, sorry, you have a change of a nucleon into a hyperon, okay? So I'm having reactions like this. And those reactions, again, you understand them whether they are possible or not, because looking at the chemical potentials, okay? So, for example, now I'm going here up. The sigma, the chemical potential of the sigma should be equal to the neutron and the electron because of the charge neutrality and also beta equilibrium in order to appear. The idea here is, for example, let's look at this plot. The idea is those quantities change with densities, okay? You have electrons, you have neutrons from the beginning, but their properties are changing because of the interactions with the medium. So the chemical potential is changing as we go more and more inside the neutron star. But at some point, it's energetically more favorable to have a sigma instead of continuing having, electrons and neutrons. That's the idea. And the first thing is, having the mass of the object. So how this relates into the star. So this is the star. So starting from, this is a model, okay? Starting from large radii going to the center. And this is the fractions of the particles, okay? So the idea here is that you begin having neutrons and protons and electrons because of charge neutrality. And as you go inside and inside and inside, it suddenly, for example, appears the sigmas. So the sigmas appear, and then there's a king in the fraction of those particles, okay? So the idea is, as I said, because of the mass difference is not so big, it might be feasible to have neutrons and protons, hyperons instead of neutrons and protons only, or electrons, okay? And this is what happens then. Well, the equation of state, the pressure versus density, or the energy per particle versus density, is softened. It means that this curvature here, if you think like something growing really fast, it grows less fast, okay? So basically, you're moving from this energy per particle and to energies of particles that it depends on the model. It could be twice less, it depends, okay? Why? Or the pressure, you see here the pressure goes up here for higher densities, but then, if you put these new particles, it goes to one of these. The difference between them is, well, some details, okay? So what it means? Well, why is this? Well, because what we call the relief of the Fermi pressure. It means that if you put a new particle there, you have is a baryon, is a Fermi particle. So basically you have a new state of particles where the energy can be shared. So basically what it means, you don't have to continue populating higher and Fermi levels, but you can populate Fermi levels which are lower in energy. And therefore the energy density, the pressure, is reduced, okay? So the system doesn't need to have this pressure, okay? Because of putting a new particle there. What it means? Well, this means that the structure of the object will change. This is kind of, a recipe of how we build, or how we determine the mass and the radius of these objects, okay, from the theoretical point of view. So basically, you have your model, which model determines your equation of state and your chemical potentials. You impose the equilibrium, this beta equilibrium and charge neutrality, and then you get your pressure of the system and the composition of the system. And once you have that, you go and think, okay, this object is what? In other static equilibrium. So basically gravity is competing with the pressure. And this is actually, if you do Newtonian analysis of the hydrostatic equilibrium, you get these ones. Forget about these parentheses, okay? So this is just assuming, that the equilibrium of forces, okay? The force of gravity versus the force associated with the pressure of the system, okay? But of course, those objects are very compact, so you have corrections of general relativity. And if you analyze and you start from the tensor, the Einstein equations, and you assume spherical symmetry of the object, you end up having, this general relativity corrections. And the idea is that you solve this, giving your favored model for the equation of state, and you get your mass and the radius of the object. This is how things are done. Of course, I said they are pulsars, so they are rotating, so there are corrections to those, okay? But the first thing you do is assuming a static object or spheric rotating with a spheric symmetry, okay? And these are actually what happens. So you have, again, I'm showing the pressure versus the energy density, and this will be the evolution with the density of the mass, okay? So now I'm saying, if I have hyperons, you don't need so much pressure. So the line goes here down. So it softens. It's what we call, we soften the equation of state. So if this happens, you don't need this high mass that you had before in order to have an equilibrium, okay, an endostatic equilibrium. So the maximum mass is reduced, okay, of these objects just by having these new particles. So, and this is what is called, for people working on strangeness in nuclear and neutron stars, is called the Hyperin puzzle. It means that if you were reaching before to solar masses, now you don't get that anymore. So you're having problems with observations. So you're having really problems that if your model before was really, giving the observations, this is what you want. I mean, not only create a model, but you want to test it. You're getting objects with less than 2 solar masses. And this is a problem. And this is a problem actually for people working with strangeness in neutron stars, okay? Solutions. So, I mean, the problem, what is the problem? The problem is hyperons is energetically probable because actually the mass is not so different, for example, of the lambda with the nucleons. However, if you have this new particle, you have a softening of the equation of state, and then you have a reduction of your maximum mass. And then, the problem is, okay, what do you do? I mean, your model is not reproducing observations, and we have really precise observations, at least of 3 events that I mentioned. So what's happening here? So your model is failing. So what do you do to improve your interactions? To really say, okay, those hyperons don't appear so early, but you push them to be higher densities so you don't find them. Or you don't have these hyperons, you have deconfined matter. Or you can solve the problem by having not only baryonic or matter, ordinary matter, but you could have dark matter. Or even your theory, of gravity is not correct. There are some modifications that you have to take into account. So there are different ways trying to solve this in order to still have strangeness in neutron stars. So this is my last, I'm going to go to my last slides. So these are, again, I mean, an example of the mass and the radius of the plots. And those lines now, I didn't mention, but they are different models. Different models that span over the whole range, you can see. Those blue ones are only nucleons. Those green ones are with with the confined strange quark matter. Those are masses observations, okay? This is one of the 2 solar mass observations. And those gray bands are areas forbidden by theory, basically. I mean, those are forbidden by general relativity. This is the Schwarzschild limit, the causality limit you have here. And this limit down here is called the mass sharing limit, basically using the fastest rotated pulsars that they know and putting some constraints on the radius and the mass because of, of this mass sharing limit, avoiding, the fact that the centrifugal force on the surface cannot exceed the gravitational force, otherwise this star disrupts. So you see that the allowed region would be somewhere here, this white area here, but still you have lots of models in that area. And there are lots of models that have these 2 solar masses. So what do we want? Really to have a radius, really to have, a measurement of a mass and radius somewhere here, or maybe even here, because then you can forget about those, okay? You can forget about those models here. So this is what my second to last slide. One of the, reasons of looking, at NICER or looking at the XTP. The idea of really have these blobs here, okay? To really have, from one side, this measurement of the mass, so we know the mass, and now to get of the same object, the radius. Those are assuming, that the radius and for objects of 1.5, of 1, or even 2. And those lines and areas are models, okay? Those red ones will be nucleonic models. Those, again, these lines here are strange quark matter models. And for example, this band here is using information of nuclear physics at low densities. and extrapolate and using information on 2 mass observations in order to constrain the area of possible observations. So the idea of obtaining these blobs here is, for example, one of the ways is this called this pulse profile modeling. So basically, the idea is to look at one of these hotspots in neutron stars and analyze the waveform, okay, this pulse profile, because this pulse profile, depending on the compactness of the object, changes, okay? And then if you know the mass, and then you can extract the compactness, you can get the radius, okay? This is one of the ways. There are others. Astroseismology, I also about using the mass shielding limit of rotating pulsars. And of course, multi-messenger astronomy. I'm not saying much more. I mean, it's just there's all these gravitational wave events, looking for more, you know, binary mergers and doing simulations and really, I mean, basically doing simulations with different equations of state and understanding whether we can extract information, whether there is a phase transition to deconfined matter, or, you know, if we have, which kind of equation of state are we dealing with? So this is just my last slide. So basically, I just wanted to show you what, from the nuclear astrophysics point of view, people have been doing. So really, one of the things is looking at the equation of state. And there has been a lot of progress, but there is still a lot of modeling. This would be, if you want, my conclusion. There are lots of challenges yet. I mean, the model dependence, of course, on the models, of course, they are model dependent. So it's because these densities we don't know, but also in order to extract experimental constraints or even astrophysical, there are also model dependencies there. There is poor knowledge of one of the parameters that we would like to be better compared by nuclear experiments. Well, this is more, you know, technical, if you want, of the 3 and 2 body forces. What I mentioned, the hyperons, whether you have them or not. And then, of course, the idea is not only to have equation of state of neutron stars, but really to model, you know, these, for example, supernovas or the binary neutron star mergers, in the sense that neutron stars, as I said, they are called objects. But of course, in supernova, you have you span over higher temperatures, and also in the binary systems of neutron star merging, you also do that. So then you really have to have an equation of state, not only at dense matter, but also temperature. And also one of the things is this isospin symmetric matter. That's the reason why the symmetry energy, the isospin, the asymmetry is so important, because neutron stars are really asymmetric. Really, the number of neutrons is much higher than protons. So, supernovas, maybe there are more symmetric systems. We don't know. So there's also, you know, this asymmetry that is also putting a problem in there. Future, nicer XTP observations, others. So really, we also need that, apart from, of course, nuclear experiments. And if you're really interested in looking, you know, and knowing what people have been doing on the equation of state, there exists a repository, an online database that is being improved thanks to this, that started with a new, with the COST, Compass Star, Newcon Star, now with Pharos. Really, we are trying, you know, this is called Discompose. We are trying, because everything started with nuclear astrophysicists, and the whole thing, you know, of moving forward Newcom Star and Pharos to really put into, you know, that people discuss not only between nuclear astrophysics, but also observationalists and people really doing, you know, looking at the observations, whether how they need the equation of state, in which way, you know, it's better for their simulations, how it can be improved, what other things apart from the equation of state they need, as for example, compositions, or if you're looking at dynamics, you know, neutron star mergers, you also need, you know, thermal conductivity, specific heat. You need other, you know, transport or not transport, you know, like coefficients that you really need to get out your model in order to really do the whole simulation and compare with observations. So thank you very much for your attention, and any questions or things, we are open. Thank you.
Thank you. Thanks a lot, Laura, for this beautiful review. Nice summary. And I have to say that I was able to follow quite a bit, even though it's not my expertise. So I think that you accomplished your goal. Is there any questions? Does somebody want to comment on something? Please raise your hands, write in the chat or whatever.
Hola.
Yes, one question,
Yes.
Laura. When you introduced the hyperons,
yes,
you mentioned like a justification values of the chemical potential, right? Is that
yes, basically.
Have anybody has done an analysis of the free energy of the system and look whether this is really the minimum of the system? Like, I mean, this is the way one should do it.
Yeah. Well, the point is, even when you
people have that.
I mean, they have analyzed, of course, the system implementing hyperons. You hear me? Yes? You hear me, Cristina? Yeah. Okay. So they have analyzed. They have analyzed I mean, if they reproduce the minimum of nuclear matter. So these hyperons appear really at 2 or 3 times saturation density. So basically, they reproduce all the, you know, the minimum energy, all the characteristics of nuclear matter, even having hyperons on the system. This is your question, I guess. So the minimum.
No, the question is whether it's really clear that it's the minimum. I'm asking just because the way you introduce the subject.
Yes.
You didn't point out to this
yes.
way of doing it, but rather to the values of the chemical potential.
Yeah, I mean, what people have done is just analyzing whether when they appear and whether at this and whether they respect still the characteristics of the system before they appear. I mean, the minimum. We are still in the minimum before they appear. Now, maybe I don't understand your question.
Okay, never mind. Yeah, I'll talk to you later.
Yeah.
Nanda has another question. Please, Nanda, go ahead.
Yes, thanks for a very nice talk. I really enjoyed it. And so my question is, I didn't get exactly what are you expecting from gravitational wave mergers, detection of other binary neutron star in order to allow somehow equation of state constraint? How does this done exactly?
There are 2 ways. People, of course, that have the possibility of doing the simulations. So basically, and then giving, you know, a variety of equations of state, and looking at the simulations whether they, you know, they fulfill the evolution, you know, this waveform and this.
But people like me that radii directly. Can you measure? Sorry? Can you measure radii directly?
There are some assumptions, I think, with this. I mean, I've seen, for example, analysis of Luciano, where they pin down maximum masses and also radius, okay, with their simulations, playing with different, a wide variety of equations of state, okay?
Yeah.
Which ones they will be allowed doing the simulation and then constraining the radius. So I've seen that, but they are doing some assumptions, okay? But people that don't have access to the simulations like me, basically what we do is look at the tidal deformability.
Yeah.
Okay.
Okay. Yeah.
So this is what we do, and then see whether we constrain at which, how we can constrain the tidal deformability, you know?
Okay. Yeah. Clear. Thanks.
Any final question, final comment?
Yeah, I would like to ask a question, just a curiosity. So, do you know whether rotation can be important or in all this business?
Yeah, there are. I mean, there are all this formulation with rotation, which is called Hartley. Well, there is a formulation of all these TOVs, but with rotation, doing some perturbation on top of this.
No, that I know.
Or Hartley, yeah.
Yeah.
So, and it could be 20%. It could be 30% corrections.
Okay.
So, yeah, why don't we do it directly? To be honest, I don't know. So, but it could be a 20-30%. Yeah. Of course, I'm thinking of really highly rotating, okay, objects. So,
Right. Yeah.
so in these cases, really. For the mass, okay?
For the mass.
Thanks a lot, Laura, for your talk, and see you all soon.
Bye-bye.
Yeah, thank you. Bye-bye.
Bye-bye. Thanks a lot.